Good morning, everyone. I'm really happy to welcome Dan Smith this morning in our seminar. So I'll briefly introduce Dan before he gives the 45-minute talks, and then we'll have a 45-minute discussion. So Dan was already speaking yesterday at the Responsible Raw Material virtual conference on byproducts from ores and mine waste. So for those who would like to watch or rewatch the talk, you can visit their website, and you can find the link of the website on our website in the section of community initiatives. I can't say that. Well, anyway, so Dan is a pure British product. Correct me if I'm wrong. He did his master's degree at the University of Leeds, and he graduated with a PhD in 2008 from the University of Leicester. His PhD was focused on an active magmatic hydrothermal systems in the Solomon Islands. And then right after his PhD, he joined the British Geological Survey, doing something a bit different from what he's currently working on. He worked on carbon capture and storage. And finally, he got back to where he came from. He got a position at the University of Leicester, where he's currently working as an associate professor in applied and environmental geosciences. Dan's interests are in magmatic and hydrothermal processes in the formation and linked with the formation of ore deposits, and especially formation of copper and gold. He's, for example, involved in the famous project. I don't know if you say it like that. So from arc magmas to ore, with Jimmy Wilkinson, for example. But today he came to present the work that that was achieved within the scope of the TC project, so tellurium and selenium, where he managed to integrate his interest in geodynamic and magmatic processes to a more in vogue topic regarding new energy and new technology. So Dan, what about Tellurium Tomorrow? I guess you can start sharing your screen, and we are ready to listen to you.
Okay, thank you very much for the introduction, and a big thank you to those of you that have followed me from yesterday's talk. In case you couldn't get enough tellurium over the last few days or even hours, and an extra big thank you to those of you that I see in the chat that actually worked on this project, who are no doubt quite sick of listening to me bang on about tellurium and its future. For the rest of you, hopefully this will be something a little bit different and a little bit new. I am going to be talking about economic geology and mineralogy, but rather than purely talking about the geology, I'm going to be talking about aspects of metallurgy and mineral supply and some of the other trappings that help to give us risk factors in the future supply of tellurium. Oops, it's a good start. I can't change my slides already. There we go. So what is tellurium used for? This is a slide that the top left image is not aging very well. For most of the 90s, tellurium was really important in rewritable optical media and also as a metallurgical additive. So the top center image shows a copper that's had tellurium added to it to make it machinable or cuttable. And metallurgical uses for tellurium as a substance which makes other metals such as lead and copper more machinable remains important. But its growth in the 21st century has really been driven by a boom in solar power, which looks likely to continue for the next 25 years and in fact accelerate over the next 25 years. And also in thermoelectric devices, which constitute about 30% of current global demand for tellurium. So thermoelectric devices don't get mentioned as much as solar panels because there are fewer beautiful stock pictures with hot air balloons of thermoelectric devices. From the top right image, you can see a thermoelectric device, and it's essentially a black square. Thermoelectric devices are ways that we can generate electricity from waste heat or use electricity for heating and, more importantly, refrigeration, so solid state refrigeration devices. So an important technology that is growing in its market share as well. But in the interests of the stock photos and availability of data, I'm going to focus on tellurium's consumption by the solar power market. So solar power is growing remarkably, so an almost exponential growth in the 21st century, and it looks set to become one of the most, if not the most important source of energy for a lot of the world's nations over the next 25 to 50 years, as many of the world's major economies and its developing economies look to seriously decarbonize their infrastructure. So solar power is something that we will need more of, and therefore we need to provide the raw materials for it. As a new technology or a technology with growing capacity, recycling is not going to meet those demands. We need mining and primary raw material supply to meet those demands. The solar panels that use tellurium specifically are a breed of solar panels known as thin film solar panels, and there are subsets within thin film technologies, and cadmium telluride, which is the main end use for the tellurium, is the biggest player in that thin film world. So thin film solar panels are lightweight, easy to use and shapeable, which gives them some inherent advantages over the silicon-based technologies, which actually dominate the market. So about somewhere between 85 and 90% of our solar panels are actually silicon-based technologies. Don't get me wrong, tellurium is important, but it's not perhaps the most important element in the world. But we can't say that because we got funding from the government. So for the purposes of the rest of the talk, tellurium is the most important element on the periodic table. And the reason why it is the most important element on the periodic table is, although those cadmium telluride solar panels are only about 10% market share, they're actually the most efficient part of the market in terms of solar power. They're just not as cheaply produced at present as some of the silicon technologies are. So cadmium telluride has some of the best energy payback time for photovoltaic and solar power systems of any of the technologies that are widely available on the market. So cadmium telluride is a really important part of our energy blend in the future. I'm sure you're familiar with diagrams like this. This is the European list of critical raw materials. So x-axis shows economic importance, so how important it is to key technologies or in general to a wider range of technologies and infrastructure and markets. And the y-axis shows supply risk. How vulnerable is that element's supply to being cut off? I'm going to filter this for a series of elements and raw materials that are important for solar power. So tellurium is often considered borderline as a critical raw material. Some years it's critical, other years it's not. And essentially it cannot respond, or the production of tellurium doesn't respond to the demand in the market because it's produced exclusively as a byproduct. But essentially it doesn't really matter whether tellurium is critical or not, because all the raw materials that go into solar panels, including the major silicon-based panels, contain critical raw materials. So if we are to continue growing solar power over the future decades, we actually need to ensure that some of these technologies move from being critical or near critical to being entirely reliable. It's a market that, in fact, almost every technology in it is susceptible to supply risk. Why does tellurium have the threat of a supply risk? Why is it considered to be critical some years? Why is it near critical? The short answer is, geologically, there's not very much of it. It's one of the rarest elements in the Earth's crust. So if I can have some nods, can you see my mouse wiggling around? Excellent. Okay, so here's tellurium down here, okay? Neighboring with our PGEs, similar order of magnitude in the Earth's crust as gold. So it's a very rare metal. Most of these metals down here, shaded in yellow, they have important uses in various industrial applications, but many of them are actually more notable for, or better known to the wider public for their use as precious metals in jewelry. Tellurium doesn't have any such use. If you were to fashion a beautiful piece of jewelry for your sweetheart out of tellurium, they would absorb some of that metalloid through their skin and gradually excrete it over the next 48 hours, and it would result in them smelling like rotting garlic. So the market for tellurium jewelry's never really taken off, which has meant that its price is relatively low compared to these these other rare metals. And of course, the price being low means that there's very little incentive for miners and metal processors to extract it. So it's rare and it's not particularly valuable. So we already start to build up our supply risks. Essentially, it's not well incentivized for recovery. Where would we recover it if we wanted to find it? Well, the short answer is that tellurium, like selenium, is in the same part of the periodic table as sulfur. And it in fact shows what we would consider to be a very strong chalcogenic behavior. I'm always confused why economic geologists use the word chalcophile to mean sulfur loving, because it actually means copper loving, and chalcogenic means it is copper. So that's the lingo, so don't blame me for it. Essentially, tellurium, like selenium, can replace sulfur in various minerals and forms. And in particular, it's in the melt that tellurium behaves more like sulfur than sulfur does. So we can see here the y-axis. This is from Brennan's work in 2015. This is the partition coefficient. We can ignore the x-axis. Really what we're looking at is that the partitioning of tellurium into a sulfide liquid over a silicate liquid is really high. So this is in log. So orders of magnitude more tellurium will move with the sulfur than with a silicate melt. This situation changes somewhat when we start to form crystalline sulfides and we form minerals. Tellurium is a big fat ion, so a lot of those crystals basically can't host it very well. So we end up with very, very exotic telluride minerals as we come down temperature. But for most of its crustal process, and certainly from mantle to crust fluxes, tellurium behaves very much like sulfur. And there's some excellent reviews that I'll point you in the direction of. So Owen Mizzen's review that came out this year covers everything you ever wanted to know about tellurium but were too afraid to ask. And Dave Holwell's got a really nice paper in Nature Comms from last year, which covers how it might move through the crust from the mantle. What we need to do to find tellurium is to look at parts of the world where we've had incredible sulfur fluxes. And this is in fact where we get most of our tellurium from now. They're from copper deposits, both VMS and porphyry deposits. The information on which deposits specifically it comes from is basically we don't have it and we don't know it. We just know it comes from reprocessing of copper deposits. In fact, we get the tellurium from the waste from these deposits. So let's explore that. So this is a photo from back when we used to be allowed outdoors. This is from the Ray porphyry deposit in Arizona, and the company that operates this, Grupo Mexico or Sarco, have historically produced significant amounts of tellurium from some of their smelting facilities, or refining facilities, I should say. So we would look at a deposit like this. We would be able to examine the ore. We would be looking particularly for the sulfide fraction. That's where our tellurium would be expected to occur, along with our copper. We would crush that rock. We would separate out the sulfide minerals. We would isolate them using gravity or perhaps by some of their surface chemistry processes using froth flotation methods. And then we would smelt it. From that smelting process, we produce a crude copper product, which is much lower in sulfur, higher in copper than the original concentrate was, something we would call a blister copper. And then we would take that to a refinery, and we would use electrolytic methods to refine it into a much higher purity of copper that we would be able to sell as what we would know and love as copper. And it's that final step when we turn the blister copper, the impure copper, into a pure copper, that the tellurium becomes concentrated enough that people start to really care about it. The process, that electrolytic process of refining the copper, produces a waste product called an anode slime. And that anode slime is rich in a whole host of byproducts: bismuth, tellurium, selenium, gold, silver, PGEs, cadmium, arsenic. A whole suite of metals and semi-metals are in there, and it has some inherent value to it, mostly because of the gold and the silver. So our refiners might sell that residue, that waste, for reprocessing, and another company might produce some gold and some silver and perhaps some tellurium out of it as well. So the amount of tellurium that we produce each year is about 500 tons of tellurium worldwide. So a very small amount of tellurium. And at present, that probably puts us into a position of slight oversupply. But we've got to bear in mind that growth of solar in the future. So this is the process in a slightly more numbers format. If our original ore had 1,000 units of tellurium, our final output of tellurium that we recover from that is about 45 units. So about 5% of the tellurium that was originally in an ore makes it through to the market. Most of the tellurium that was originally in the ore basically goes to the tailings. We'll go through why that is in a second. And what we shouldn't forget is that this whole process isn't driven by the recovery of tellurium. Up to here, it's driven by the recovery of copper. And from this point on, this is driven by gold and PGEs. So the price, the demand, and the costs of the recovery of gold, silver, and the PGEs affect tellurium. The price of tellurium very rarely affects tellurium. There is an alternative way of processing copper, though, and that is to not bother separating it after you've crushed it, and to not bother sending it to a smelter, and then to not bother sending that blister copper to a refinery. An alternative method, which is more relevant for highly oxidized ores or for very low-grade ores that many of our porphyry deposits are now facing, is to heap leach them. Essentially, we would crush them, form them into piles or pads, and we would essentially leach them or trickle through a solvent which would remove some, probably not all, but some of that copper. That route, heap leaching, has absolutely zero potential for recovering tellurium. Each of these steps in the normal processing of copper lead to a progressive enrichment of the sum of the units of tellurium there, until it's weight percent by the time we get to an anode slime. In heap leaching, we never arrive at that point with weight percent of tellurium, so it's never recoverable. These heap leaching operations are an important part of our copper supply. If people aren't aware of the scale of mining, and it's always worth us reminding ourselves just what the scale of mining is, there's a little infographic. So this is Escondida in Chile, and this square or rectangular looking facility down here, these are the leach pads for processing low-grade sulfide ore. I'm not much of a runner. It would take me at least an hour to get around those. They are 10 kilometers by perimeter. This is the leach pad here. And for a sense of scale, this is the city of Leicester at exactly the same scale. So our neighborhood, our city center, most of our green space in the city could easily fit within those leach pad facilities. These are enormous industrial enterprises. We are not going to convince the mining industry to do something different to process the ore just for the sake of a few tons of tellurium. This is the way it works and the way it's going to be. And it's something that has increased steadily through the back half of the 20th century. Heap leaching has really become a significant part of global copper production. And the net result of that is that tellurium production has actually decreased. Although we need more of it now than we ever did, 70% of the demand for tellurium didn't exist before the year 2000. So thermoelectric devices, solar panels, in cadmium telluride photovoltaic cells. We've seen a progressive drop of what we would call the byproduct intensity of copper ore. And I've had a look at some other elements as well. I can't recall them off the top of my head, so I don't want to embarrass myself on a permanent record on YouTube. But the byproduct intensity of copper has declined for a number of metals. What we would consider our critical, our technology metals. It's not that we're becoming less efficient at extracting them, it's that we've prioritized methods of extraction that don't favor them. So as part of our project, we did look at some copper ore, but it turned out not really to be very exciting for the TEAS project. Katie McFall, who's in the list of participants, will probably disagree with me here because she looked at some fabulously tellurium-enriched porphyry deposits. But some of the ones that we looked at from the Leicester team were pretty boring. In fact, the association with copper ore is a little bit weak. It's probably better that we describe tellurium as being associated with sulfide ores in general. And many of the sites that we looked at, we didn't find a particularly high concentration of tellurium in the copper-rich minerals, certainly not in chalcopyrite, which is the dominant copper mineral for most of the deposits that we looked at. Instead, what we were seeing is tellurium minerals in association with that ore, but not with the chalcopyrite. In fact, in a lot of locations, what we find is that pyrite is actually the most abundant and important host for tellurium. We find that bulk ore values and pyrite values strongly overlap in terms of concentration. In other words, the tellurium content of pyrite is basically the proxy, or is the tellurium content of the rocks. So pyrite is a key part of it. Pyrite can be quite a dirty element in terms of its trace element record, and this is something that in the age of laser ablation ICP-MS that we're getting a much better handle of, and we're seeing that pyrite can be an important part of controlling the trace metal assemblage of an ore. The problem is that pyrite is actually a really difficult mineral to process, not least because one of the main mechanisms by which pyrite becomes enriched in trace metals is by essentially a lattice deformation effect, where arsenic substitutes into the pyrite lattice. So to recover tellurium, gold, bismuth, other metals that we're interested in from pyrite, we're also going to be extracting arsenic, which has obvious toxic effects in the environment. Also, other metals would accompany those critical metals that we're interested in, things like mercury. So we risk, by processing that pyrite, generating more problems or more hazardous waste that we would then be obliged to process further. Whereas in the pyrite, it's perhaps more dilute and more manageable. Its association with pyrite, or tellurium's association with pyrite, to bring us back on topic, probably explains why most units of tellurium from an ore don't make it through to being a product, why most of them get sent to the tailings. Essentially, our mining or mineral processing operations are optimized to remove the non-copper minerals, and tellurium is in those non-copper minerals. So our supply route for tellurium is really quite vulnerable here. We could potentially improve these routes, but let's not forget that tellurium is really not in the right minerals that we want to process here. So it's a hard ask to get industry to optimize for this. A price rise in tellurium might stimulate a change of behavior, but a price rise in tellurium would also make our solar panels much more expensive. And they're really something that we want to be as cheap as possible, to be competitive with fossil fuels, other solar power mechanisms, wind power, etc. So what's the waste and potential? What can we do with tellurium? What's the current state of affairs? Tellurium is not well recovered from copper deposits, but to be honest, it's not actually that abundant in many of those copper resources. Many of the world's porphyries are not analyzed for tellurium, but realistically, we're looking at a presence of tellurium that's the same order of magnitude as gold. So we're looking at a gram per ton or less, and probably for many of them, we're into the parts per billion range. The waste from porphyries and perhaps more importantly, VMS deposits, as smaller, higher grade deposits, they might be fruitful for tellurium, but probably not. A lot of our tellurium is probably bound up in a whole catalogue of complex, weird, impossible to remember telluride minerals that are difficult to process, or it's bound in more abundantly in uneconomic pyrite. A price rise for tellurium might incentivize recovery, but it will probably reduce consumption too. So what we need as a society, or to support the solar industries, are tellurium sources in which the tellurium can be targeted, so we know where it is and we know exactly what form it's going to be in. It co-occurs with a desirable metal, therefore our other industrial operations are going to concentrate it without too much further incentivization. It needs to be enriched, so high grade, and it needs to be in a form that can be recovered. Fortunately, we know what that is, and we've known what that is for maybe 100 years. Okay, so the most important repositories or concentrations of telluride minerals and tellurium on the Earth's crust are actually gold deposits, hydrothermal ore deposits in particular, orogenic gold, epithermal gold, and particularly some subsets of epithermal gold. So the current world resource base, I use the words reserve and resource very loosely here. These are simply an estimation based on copper production and ratio of tellurium from copper production, which is the USGS method for doing an inventory or a stock take of tellurium. They're not reserves and resources by the strict definition, but essentially the amount of tellurium that we would likely recover from copper, we could replace that by targeting maybe a dozen gold deposits. At present, there's only one gold deposit in the world which produces tellurium, and that's Kankberg in Sweden. It's the world's only tellurium reserve with a resource code reporting it. It contains about 700 tons of tellurium, roughly. And it's the only place in the world that officially has tellurium to a resource reported standard. Okay, so instead of looking at our porphyry deposits or VMS deposits, we will be looking perhaps shallower in the crust. I'm going to focus in on the epithermal deposits. These are some of the ones that have perhaps the most famous association with telluride mineralization. So of course we have high sulfidation deposits which can show a trace amount of telluride minerals. So these are epithermal deposits which have a direct connection, a direct genetic link to shallow subsurface magmatism. So they're usually hosted within volcanic edifices and are roughly synchronous with volcanic activity or immediately after volcanic activity. And then there are our low sulfidation deposits which have perhaps a weaker link to direct magmatism and the input and influx of magmatic volatiles, and usually are delayed with relation to volcanic activity. The deposits would typically look something like this for low sulfidation deposits. So intense quartz veining, intense hydrothermal alteration of lithologies within the top a few hundred meters, maybe down to a couple of kilometers of the Earth's surface. And we would be looking in these veins for very fine sulfides, visible gold, electrum, maybe non-visible gold as well. Okay, and potentially tellurides. So some classic textures of epithermal, low sulfidation epithermal veins. I'm showing these deliberately because tellurium deposits don't tend to look like this. Our telluride rich deposits that are low sulfidation deposits, they're very different beasts. So essentially there's a subclassification of our epithermal deposits. If it wasn't confusing enough with adularia cerussite type, acid sulfate type, high sulfidation, low sulfidation, intermediate sulfidation, two different definitions of what sulfidation means, there is another class out there, and that's the alkalic deposits. This is a compilation that Ed Dubray put together, showing what the host rocks of most of the world's epithermal deposits are. So high sulfidation in red, low sulfidation in blue, a vast sweep of what we would consider normal volcanic or shallow intrusive rocks, basalts through to dacites, and perhaps more concentrated in the andesites. Those are not the hosts for our tellurides. Our really telluride-rich deposits are those ones that sit above that alkaline line. Cripple Creek in Colorado is a world-class example of a gold telluride deposit, and that's phonolithic. Lihir has significant amounts of tellurium, mostly in pyrite in Lihir. That's trachytic or trachyandesitic. And then we have famous deposits such as Vatakula, used to be known as Emperor in Fiji, which actually produced tellurium for a number of years in the 70s, Bulgaria in Papua New Guinea. We have an association of some of the world's most notable gold deposits that are actually really significant gold telluride deposits and the alkaline. So here they are in terms of gold. Sure, many of you are more interested in the gold than the tellurium, and essentially some of the world's top 10 best endowed, highest grade, biggest tonnage gold deposits are actually hosted in alkaline rocks, not in our normal calc-alkaline to tholeiitic compositions that we typically see in volcanic arcs and margins. They have some tectonic associations too, so if you look at Dave Holwell's paper from 2019, he explores some of that as well. So this is Cripple Creek. This is in Colorado. It's a phenomenal mine. It's a huge pit. Now extracting quite a lot of their gold by heap leach processing. So they're in some quite low grade portions of the deposit now, but it's been you know, a producing world-class deposit for over 100 years. So here are the heap leach pads. In this case, they're using a dilute cyanide solution to extract the gold. And this is probably suboptimal for a telluride deposit. The telluride deposits are actually quite difficult metallurgical beasts to process. Telluride minerals don't behave the same way as native gold or electrum, and there's lots of issues with passivation of solvents and insolubility of the gold in those systems. So recovery from gold telluride deposits isn't as good as some of the smaller, lower grade deposits that dominate our list of world-class deposits. So they have their own challenges. And unlike some of the textures that we saw before, where we saw huge amounts of quartz veining and not particularly showy amounts of sulfides or obvious ore mineralization in some of those other deposits I showed you from New Zealand and Greece, our geology from Cripple Creek looks like this. So there's very little quartz in these rocks. There's very little quartz veining. There is some quartz veining in Cripple Creek, but it's nowhere near as intense as what we would associate with a classic low sulfidation ore deposit texture. We can see here there's a lot of fluorite in these rocks. There's quite a lot of carbonate in there. It's less visible on this photograph. There's a lot of pyrite in there. There is gold and electrum, but the main ore mineral that you can see here is actually calaverite and sylvanite. So gold and gold-silver tellurides. They have a very different texture and they have a very different mineralogy. They have a very different host rock. So one of the things that we've really been interested in our group is whether being in an alkaline rock makes you a telluride deposit. Is it something as simple and as crude as that? And you would think that this would be a very old question that we would understand. And it turns out perhaps not. So I did some work where I essentially modeled what would happen if you tried to make a high sulfidation deposit. So you pumped acidic volcanic gases and brines or liquids through some of these alkaline rocks, like a phonolite at Cripple Creek. Let's have a look at what happens to them. It turns out that if you try to make a high sulfidation deposit in an alkaline rock, it's not a problem. So at very acidic levels, we get very acidic type alteration. We get very acidic pHs, and the alteration assemblages down here, I'll show you those in the next slide, we produce a high sulfidation type alteration system. It's when we get to this low sulfidation end where we're dealing with more rock buffered fluid compositions that we see a big difference in how a phonolite or a Cripple Creek type rock behaves than a normal andesite, dacite or basalt. The difference between basalt, andesite, dacite on here, by the way, is trivial. They all max out at what a geothermal scientist or somebody who's well steeped in the history of epithermal alteration would describe as a near neutral chloride fluid. For those of you that are more used to looking at the solids rather than the liquids in an epithermal deposit, these are the conditions on which we form propylitic alteration. So our feldspars tend to survive. We get a small amount of carbonate surviving, and essentially we're turning our mafic minerals into chloride. These conditions up here are abnormal, and these are our alkaline rocks. Our phonolite at the top, a Luis phonolite from the Ladalam system up here, and we get these breakout pHs. This is at 300 degrees, so pH 6 is neutrality, approximately speaking, at 300 degrees. pH 8 is definitely alkaline. And what we see is still a form of propylitic alteration. I will show you the minerals in just a second. But the key thing here is that when we end up with a rock buffered fluid composition, we've got a very different pH in this subset of deposits. So bearing in mind, this covers some of the world's largest gold deposits. Our normal alteration, when we pump a fluid through a rock, we would expect to see, this is essentially from the volcanic gas through to a low sulfidation type quartz vein on the periphery of a system. Our mineralization we would probably expect to be in some sort of sericitic alteration type assemblage, which would probably cut through about this sort of paragenetic sequence here. Okay, so if it's in black, that means it's really abundant. If it's in gray, it means it's slightly less abundant, but it's showing you where the peaks of the minerals are. Important to note, if you try to generate any kind of epithermal alteration in a normal andesite or a basalt dacite or rhyolite, you end up with a lot of quartz. Quartz is ubiquitous. Quick hands up in the Zoom chat, who's seen quartz veining? Okay, I got at least 3 hands up there, but I can only see 4 windows. So quartz veining is common. It's kind of what we expect, and it's what we would actually look for if we were Oh, somebody's digitally raised their hand now. Thank you very much. Thank you very much, Alexandra. Quartz veining is what we look for and what we explore for, and it forms resistant high grounds in epithermal terrain. So it gives our exploration geologists these great outcrops and targets that they can home in on. They don't even have to go and look at them. They can see them from LiDAR surveys. You know, they stick. And we end up at our propylitic alteration where we've got feldspar stable, some epidote, lots of chlorite, still lots of quartz. When we look at our phonolites, okay, we still have propylitic alteration. We still have, there's a little bit of epidote there. It is there, believe me, it's just not very big. There's a little bit of carbonate there, perhaps a little bit more than on this side. Carbonate's very influenced by how much calcium is in the rock, actually. Feldspar is still surviving, chlorite's still there. The really important thing here, who'd have thunk it, the most important mineral to a gold telluride deposit is actually quartz. Our alkaline deposits are notably quartz poor. They're not quartz free. There are big parts of them that do have quartz veining, but they don't have these massive zones of silicification and intense quartz cutting chalcedony, cutting quartz, cutting chalcedony type vein structures. It's not there. Something different goes on in these deposits. Essentially, they run out of silica and they can no longer precipitate quartz. Just to show you the differences. We get some more exotic minerals appear to some zeolites, feldspathoids, etc. So apologies for the chemistry so early in the morning or at beer time, depending on where in the world you are. There are a couple of buffers which are really important to controlling pH. In a normal calc-alkaline system with silica saturated andesite, this is a buffer that controls pH, and basically it does not run out. There is always enough of these 4 minerals that once you reach pH 6 at 300 degrees C, there you stay. And you end up with quartz veining and propylitic alteration. This is the fluid that does most of the work. When we look at our alkaline systems, we've run out of quartz essentially, and we shift onto new buffers with new minerals. We're still feldspar stable, but we're getting some slightly more exotic minerals in there that are reported in places like Cripple Creek. So we can empirically verify some of this as well. And it's not necessarily the alkali content of the rocks that's important. It's not the sodium and potassium content. It's the silica content for the amount of calcium, aluminium, sodium, and potassium that's available. Something that a petrologist would refer to as the silica saturation index. Essentially, most of the rocks that we deal with as when we're looking for epithermal or porphyry deposits, silica saturated rocks. They don't necessarily have quartz phenocrysts in them, many of them do, but they're silica saturated. Essentially, the low temperature equilibrium version of those rocks always has quartz in it. That is not the case for some of the samples that we're looking at in Fiji, Colorado, Papua New Guinea. Okay, and they end up with this much higher pH. Okay, so fluid pH, does that matter? It's affecting our exploration targets. We no longer have quartz hard grounds. We no longer have intense veining to look at. It affects our processing. We don't have quartz. We've got a lot of carbonate, which can cause us problems for some methods. And it's probably also the mechanism by which we arrive at gold telluride stability. So this is a wonderful piece of work that came out of Joel Brugger's group. So Grundler published this in 2013. So it's essentially a heat map showing the solubility and stability of different tellurium phases. And the gray circle here is the stability of the gold bisulfide phase. So our normal host rocks for epithermal deposits would produce a fluid that would sit here. So it's in gold bisulfide stability, a moderate pH, perhaps extending a little bit lower as part of the working fluid, but it's the absolute nadir of tellurium stability, of tellurium solubility. So essentially, most epithermal deposits do not move tellurium around. They cannot focus it, they cannot concentrate it, and therefore they cannot precipitate it into volumes of rock at higher grades. Our alkaline hosted deposits still sit in gold bisulfide stability fields, so they can move gold around, but they are orders of magnitude more successful or more capable of moving tellurium around in their fluids. So it's the host rocks that can actually produce an important effect of moving gold and tellurium at the same time and allowing them to co-precipitate. Now they're co-precipitated, we have to find a way of getting them apart. Tellurium is one of the very few elements on the periodic table that will actually form stable minerals with gold, and it forms a lot of different stable minerals with gold, different polymorphs and different combinations with silver, lots of different sulfur salts. So this, although it produces high-grade gold, or can produce high-grade gold, and it usually mirrors that gold grade with tellurium grade, it causes us some exploration problems in terms of those quartz targets, but also some processing problems in terms of the tellurium causing problems for gold extraction. We end up with beautiful assemblages like this. So this is calcite growing on a wall rock of roscolite, rich altered absaracite. Brace yourself for the terms. That's a potassic rock from Vatakula mine in Fiji. And on the surface of those calcites, we're getting a wire gold. So a really high grade piece of rock here. And tellurides are usually not very spectacular. In fact, most of the time we need an SEM to see them. Some of the background here is a little bit sparkly. It's a mixture of calcite, and there are some tellurides there. Sometimes the tellurides are absolutely beautiful. Sadly, this is a sample that remained on the geologist that found its bookshelf, and he wouldn't give it to me, though I think I deserve it. This is silvanite. So this is a silver gold telluride from Vatakula. Beautiful crystals of the stuff, and you can get a sense of the scale of them. These are about 1 centimeter to 1.5 centimeters long, next to some calcite rhombs, next to some gold. Fabulous high-grade assemblage. Okay, but if you were to try and process that by a conventional method for extracting that gold or that gold there, you would not touch this. It would not dissolve in the same fluids. And in fact, what would happen is that this would start reprecipitating native tellurium onto the surface of that gold and reduce your gold solubility. So a nightmare to process. So we know what the deposits are that have potential. We've got a geological system which looks like it's far more effective at bringing in tellurium, and Dave's got some interesting stuff that he might talk to you in the future about how it might move through the crust as well. But certainly when we get to the mid to upper crust, we can generate fluids in these alkaline rocks, which are much more suitable working fluids for getting tellurium into veins and then getting it to co-occur with the minerals. The challenge here is, how do we extract the stuff? How do we get it out? This is a problem, and it's not just a problem for the tellurium, it's actually a problem for the gold and the silver as well. So what we've been working on at Leicester is a different solvents. We've been working on a form of solvent with our colleagues in chemistry called deep eutectic solvents. These are anhydrous salts. Essentially, we mix two salts together and they form a eutectic, a lower melting point, and they become a liquid at room temperature. And these become very powerful solvents. Because there's no water in them, they don't form oxides and hydroxides with the metals. Okay, most mineral acids are dissolved in water, and water is very reactive with the metals, and it forms oxyhydroxides, which are more stable versions of those metals. Therefore, they passivate themselves. These salts, they have a high ligand concentration, so they have the solubility properties of fairly concentrated acids with none of the downsides of having lots of water in there. And we construct them by mixing organic salts such as choline chloride and a hydrogen bond donor. And we can use common chemicals such as urea. So we can produce these pretty cheaply. And we've got about 1 million of them patented. Sadly, that's not me, that's our chemists. So just to show you an example of how these compare, water is an effective solvent. mostly because of its polar properties. It gets more effective if we add something like HCl. The chloride behaves as a ligand and enhances the solubility of metals. But even at very high concentrations, so 38% hydrochloric acid, a strong mineral acid, or a powerful mineral acid, I should rather say, we still have a huge molarity of water. And that water acts as both a solvent and a passivant, depending on what state the metal is in. Eventually, it will react with the metals to form stable, insoluble oxyhydroxides. Our deep eutectic solvents, they retain some of that ligand concentration of a fairly strong acid with none of that water to passivate the system. So let's hope this works. Videos within videos. Just in case people don't know what mixing two solids to produce a liquid looks like, these are stable solids, in which case they are fairly safe, or they are safe to store and transport, easier to store and transport than liquids. We mix them together and we produce this deep eutectic solvent. These have a low vapor pressure, so they don't smell, they don't release gases, and they're mixed from non-toxic, fairly environmentally benign substances. So those substances include choline chloride, which is produced on the megaton scale around the world. It's vitamin B4. The image there might make you think that it's made from baby chickens, the cutest ones. We don't make it from the baby chickens, we make it for the baby chickens. It's a food additive. Okay, so the agricultural industry produces it by the thousands of tons in most of the world's countries. Urea is the other constituent that we use, particularly for solubilizing gold in our solvents. This is a common fertilizer, so it's cheap. We're dealing with non-toxic, biodegradable, non-flammable substances that can be disposed of by raising them in temperature to about 300 degrees C. They'll break down to essentially water, nitrogen, and CO2. So we can dispose of these substances as well. We can actually recycle them. Because what we're doing when we process our minerals is we're doing electrochemistry. We often introduce a catalyst, so we've been using iodine with gold. What it allows us to do is to tinker with the voltage. Don't ask me any difficult questions about electrochemistry. I am a geologist. I'm overreaching myself by presenting some of this content. But we can use electrochemistry to select different voltages to essentially precipitate out different metals, so gold versus silver or gold versus tellurium. And it allows us to solubilize, our solvents allow us to solubilize a whole range of minerals. They're very powerful solvents, but very safe for the workplace. When we first started this project and we started discussing these solvents with our collaborators in the mining industry, we got it totally wrong, because we went with the assumption that cyanide is an unsafe substance. Quick show of hands, who's heard of cyanide and thinks it's dangerous? It's actually handled very, thank you very much, Alexandra, my go-to digital hand raiser. Cyanide is actually handled very safely, a huge amount in the industry, and we made a terrible blunder with industry when we said, oh, cyanide's not safe. It's a very common perception, but that common perception is cyanide's problem. Cyanide has very low public acceptability, particularly in the EU, and particularly in Romania, in fact. And Romania is Europe's biggest accumulation of gold telluride deposits in a post-subduction and mildly alkaline volcanic complexes. In fact, a number of our telluride minerals that I've been talking about, sylvanite is named for Transylvania. It's named for the Romanian locations where it was first described. So this is a European problem as well as a Colorado problem or a Fiji problem. And cyanide people are aware of it and they don't like it. And it doesn't matter how safe it is. Thank you to people like Agatha Christie, we all know that it's poisonous. And it doesn't really matter how safely you can handle it anymore. So industry needs to look for ways to replace it. So how does it work? Well, we've been assessing this at test tube and beaker scale. So we're not up to processing our 16 million ounce deposits quite yet. So this is a view of a petrographic block in 3D, so a three-dimensional microscope. So what we can see is pyrite. So remember, pyrite sometimes contains our tellurium, but more often than not, we don't want to process pyrite because it's rich in arsenic. Sometimes we do. With our solvents, what we can do is tinker with the catalysts that we're putting in and choose whether or not pyrite dissolves or not. So this is electrum cutting, an electrum vein cutting through pyrite. We introduce our solvent. 5 minutes later, at room temperature, the gold is dissolved out, and then it can be precipitated by electrochemistry. We can show this for different mineral assemblages. So galena pyrite, quartz, electrum. So this is an in situ leach, again, a polished block. And we can see that after 10 minutes, 50 degrees C, so slightly above room temperature in this case, we've selectively dissolved out the gold. So gold solubility is actually faster in these solvents than it is in cyanide. And it's allowing us to target the minerals that we really want, including minerals like gold, telluride, calaverite. So slightly less soluble than the gold. So we're seeing an etching effect here rather than a full dissolution after the timing of this experiment. But it's showing promise, better than cyanide would do for calaverite. Basically, calaverite would be more or less insoluble in that solution. So we think we're onto something here, and it's an ongoing piece of work and something that we are continuing to look for partnerships and collaborations for. We've discovered or developed solvents which are cheap, environmentally benign and effective for some of the minerals that we're interested in. And really crucially, and why I've introduced it in this talk, is that they have the potential for recovering byproducts from polymineralic ores or concentrates that we would traditionally have considered to be quite dirty and metallurgically difficult to process. And it might allow us to unlock deposits which have traditionally been very difficult to process because they've got refractory minerals in. Those refractory minerals are the ones that we're really interested in. I'm really interested in. They're the gold tellurides. So in the future, what are we looking at? Well, tellurium is going to remain a key part of the future expansion of solar power, particularly as we start to attach solar panels to more than just our houses. If we start to attach them onto cars or onto different surfaces, thin film is really the route to doing that. It's a lightweight photovoltaic technology. There is some potential or scope for increasing recovery from the sources we currently process, but they're not the best geological sources. They're not the ones where nature has pre-enriched the tellurium for us. And in some cases, they're not ideal geometallurgically to process. The minerals aren't in the right place, and they end up in refractory or toxic or difficult to process forms. So essentially, to recover the tellurium, we'll be putting the cost up for the mineral processors, and that's something that they probably will not accept. We know what our alternative geological sources are, and I won't pretend that that's my discovery, that these deposits are telluride rich. We've known about that for decades. We know they might be a better source. Our challenge has always been, how do we process them? So the challenge for us as a community, as a society, as researchers, is to not just find deposits, but find deposits that we can process. And if we can't process them, then we need to work with our colleagues in chemistry, metallurgy, engineering to figure out new methods of processing ores, so we avoid waste and we avoid vital environmental technologies failing. So that's me. I'd just like to thank some of my many collaborators on this project, from academia, industry, private sector, public sector, and then just for the sake of YouTube, some useful papers that you might be interested in, most if not all of which are open access, that you can look at, and not all of them include me as an author. And down at the bottom, rather than pick out individual papers, I've picked out some authors who are world experts in tellurium, selenium, and other exotic metals and minerals that you might be interested in if you enjoyed this talk. Thank you very much.